So let's start. So we have a slightly different kind of talk today. We'll be after Tousif Islam, we'll be talking about accelerating gravitational waves inference. So this is about computation applied to physics. So Tousif is a Kavli postdoctoral scholar at the Kavli Institute, the well-known Kavli Institute at the University of California, Santa Barbara. His research focuses on high-performance computing, data science, and gravitational wave astronomy. He did his PhD at University of Massachusetts Dartmouth, and since then he's been at PhD. During his PhD, he had several research fellowships, including the Kavli Graduate Fellow at UCSD, pre-doctoral scholar at the LSF Institute for Pure and Applied Mathematics at UCLA, and a visiting researcher at the Tousif Group at Caltech, semester at ICER and Brown, and was a cabinet fellow at the Niels Bohr Institute at Copenhagen. Before that, he was a BSMS student in physics at IISER in Kolkata, and a long-term student fellow at ICPSTFR. He also describes himself on his page in my Hindi accented Bengali as Tather Gamkesh. So we'll see some of those.
Yeah, thanks for pretty nice to that. Thanks for coming here for this talk today. I understand that this is a different audience and more theoretically oriented computer science people, but still I thought it may be a nice opportunity to discuss some of the computational sciences that we are doing for gravitational waves astronomy. So I'll start with a brief overview of the gravitational wave sciences so that we understand what we are doing and why we are doing those things. And then I will describe the modeling. So the modeling here is more or less the time series modeling using the reduced order surrogates. And I will describe some of the state-of-art things that we do and what we are doing for the coming years. And I'll describe some of those details. Okay, but like if you have questions or anything, please feel free to stop me and ask those. Okay, so hopefully this is. Okay, this is what is that. Okay, perfect. So I work in different areas in gravitational waves. One of them is doing numerical relativity that actually does the simulation of the binary black hole mergers. So you have two black holes, they are merging, and you could describe that merger using Einstein's equations and all these, and you evolve the whole systems, solve the partial differential equations, get the solution that is what we call the numerical relativity. And we use those simulations and then we build the surrogates so that we can use those surrogates because they are much faster in the gravitational wave sciences. And then we also do something called the black hole perturbation theory simulation. So where you approximate the numerical relativity in some way and then solve the equations again with the approximations. And then because they are also a little bit expensive, so we build another kind of surrogates for those kind of things. And then I use those surrogates to do the gravitational wave data analysis. And I also have interest in building some Bayesian framework with physics input so that it's faster and more efficient in sampling the parameters that describes the binary black holes. And I use those kind of things. However, mostly I'll talk about the numerical relativity surrogates and what we are doing there. Okay, and these are the set of people with whom I mostly work with on different kind of surrogates and the data analysis perspective. Mostly Scott Field, who was my advisor at University of Dartmouth and who was one of the person behind the surrogate, which he started when he was a postdoc at the University of Maryland, and things started from there. Okay, and these are other sets of people with whom I do the analysis and the black hole perturbation theory simulations. Okay. All right, so first we'll start with a very quick and brief overview of the gravitational wave sciences. So we have we are currently using the 4 or 5 detectors that we have throughout the world and within the LIGO Virgo Kagra collaboration. So we have 2 detectors in the US, one in the Hanford and one in Livingston. Then we have one detector in Europe, and then there's one planned in India, and there's some work going on there. And there was one detector in Japan called Kagra, but something happened to that detector because of earthquakes and all. So it's not really operational in that way. But these are the like set of people, like around 1,000 researchers from like 18, 20 countries working under the same umbrella, working for the gravitational wave sciences. Okay. And this is just an like if you go to one of the observatories where we actually have the detector, it looks something like that in the middle of the desert. And we have like a almost like it's a L-shaped detector, and one of the arms you could see it's like around 4 kilometers long. And in that vacuum we have different kind of instruments that actually detects the gravitational waves. And when we call about the gravitational waves, the first thing we'll start with the numerical simulations as described by the general relativity proposed by Einstein. And those simulations are pretty expensive because we simulate the exact Einstein according to the exact Einstein's equations, and it typically takes like a day to many months, depending on the complexity of the physics that involves in the binary modules. And typically we use different supercomputers. Most of our allocation was in Frontier, one of the supercomputer in the US, and where we used to do most of our simulations. Okay, so now I'll just show two of the simulations in a, like if two black holes are merging and you are looking from above, this is how it looks like. So you have two black holes, which are more or less the two black objects. They are inspiraling against each other. And as they inspiral, they emit the radiation. And that also means that as they emit the radiation, their orbit shrinks. And at some point, they would just merge into each other, and they will create a new black hole. So that's more or less the scenario we are talking about. Okay, and then we could look at similar simulations again, but now instead of looking ahead, you are looking from an angle, and this is how the space-time looks like. So in Einstein's general relativity, when you have everything is a space-time, and there are two black holes that deform the space-time, and as they merge, what happens is that there is a ripple in the space-time, and that's what is the gravitational waves. And we can probably play it again.
So this yellow and blue depicts the gravitational wave?
Yeah, so that's the strength of the ripples. Yeah, yes. Oh, sorry. Maybe I can. Yes. So here you could see that as they're merging and as they're inserting in each other, so there's also a line that is going. So that's how the radiation looks like as as a function of time. So that's the kind of time series we get out of the binary graph merger. And towards the end, this is where there is a peak in the time series. That's where the merger happens, and you get the maximum radiation. And after that, there's unstable black hole, so that then radiates further to get back to some normalcy, and that's another set of radiation that we have.
I have a very quick question. So in this picture, what is the medium in some sense? So what is the crest and the trough for denoting, and what is the yellow and the blue denoting?
Oh, okay. So I think yellow and blue denoting this like the amplitudes in some sense here. Okay. So this is a time series in this. So we have a okay. So in GR there are two different polarization. So each are real value time series. So we typically describe them as like a complex number. So the whole time series we describe them as a complex number. So now we are looking at the real part of that. Let's say, and so these time series. So these are the yellow and the blue here, which corresponds to these ups and downs in the radiation time series. Basically, it's growing, and then this would mean that, and also as the time progresses, the frequency of the whole system would also increase, and this would be where they would merge and would have the maximum amplitude. Is that what you are asking?
I guess what I think is even more stupid. So I guess when so this way there's a crest and there's a trough, right?
Yes.
So what does the crest mean and what does the trough mean?
Okay.
So it's essentially Gaussian space-time that's being perturbed by this, if you want to think about that. So we have, right now, there are no gravitational wave passing. So what we are supposed to be in a, according to, where the special relativity and things like work, you can consider this as Minkowskian.
So it's a space which is contracting. And
Yes, and
Oh,
the part of
okay.
that part of the, it's a flat, and the gravitational waves kind of changes, that space-time in a, that's given by this. Does that make sense to you?
There is no medium.
Yeah.
There is
Yeah.
it is a space.
So these are like happening in vacuum.
Yeah, so I guess if I understand correctly, it's something it means where the space is contracting and expanding.
Yeah, essentially. So
Yeah,
that's,
yeah, free particles. I think that part is easily. So you have free particles in as a circle, and they will they will move without any force.
Without any force, right.
Just because the space is.
So that
Sorry.
straight line after that is supposed to be the Minkowskian space-time,
Got it.
if you want to think in terms of.
Thank you.
Okay. Yeah. All right. So then, just to give a sense of the scales associated with this problem, so one of the first binary black hole merger that we detected around in 2015. So there were two black holes. Roughly, the masses of the two black holes were around like 36 solar mass and around 30 solar mass, and they were around 200 kilometer wide. Both the black holes, and they merged. So initially they were around 500 to 1,000 kilometer away from each other, and they were rotating at in the orbit with a rate of around 15 times per second. And as the time progresses, you could see that they started moving faster, and that rate would become like 250 times per second. And then finally they would merge and create a new black hole, which is very close to the sum of the two masses of the black hole. And some of the mass would be radiated away, but apart from that, we will have like around 60 solar mass in the final black hole, which was around 230 kilometer wide. So this is the time scale we have, and this is happening for binary black hole mergers. When we have two black holes of tens of solar masses, this will happen within 1 second-ish time frame. Okay, and the kind of ripples or gravitational waves we are talking about, if you have an atom and you kind of have a mindset like how like what would be the size of an atom, the ripples we are talking about would be 1 billion times smaller than an atom, and that's what we would be seeing on the detector, and that's what we would be using to infer the astrophysics of the black holes or the binary black holes. So when we model things, we have to be really precise so that we can model them accurately and we are not biased or wrong. Okay, so now what we will do is that we will look at the different time series. So these are the radiation time series coming out of the binary black hole merger problem, and we call them the waveforms. So going forward, many times I'll just call it waveforms, and which would mean this radiation time series that I'm showing here. And these are the different variety of the radiation time series that you may get out of the binary black hole mergers, depending on the physics that is involved in the system. So let's say you have two black holes and they have no spin. So both of them are non-spinning and they are just inspiraling and merging. So in that case, you would get the first one. And then what you can do is that you can give both the black holes a little bit of spin so that they could only spin in a way that their spin axis is aligned with the total angular momentum axis of the system. In that case, what you will get very similar to the first one. So that's shown here. Now you can say that, okay, my two black holes, they are still spinning with this aligned angular momentum thing, but I would allow them to be in an elliptical orbit instead of a circular orbit. In that case, the radiation time series would become slightly more complex than these two, and you will start seeing more modulations in your time series, and things would start becoming more difficult. And then you could also say that, okay, I would now allow the two black holes to be spinning in any direction. So in the three-dimensional space, their spin axis could be directing to anywhere. And in that case, you will get something like this one. And when you combine these two, it would be even more complex in terms of the morphology And which means that your modeling would become much more difficult. Your analysis, like once you detect some signal and you want to compare it with some known physics or templates, you may come up with different physics. That would also become difficult when you include all of these physics together.
So this orange waveform is like this because they are in elliptical orbit, so they are sometimes closer together. Then you have this high frequency.
Yes. Yeah. So these ones.
And then you have they are farther away. You have this slower
radiation. Right. Yes. So these ups and downs are corresponding to those 2 points. Yes.
So I'm still stuck on the previous slide. Can you switch back? You say that that's the size of gravitational wave.
Yeah, like the okay. So if you calculate the gravitational wave time series, like the amplitude of that would be of that order. It's not really a size. I mean, it was yes, definitely, yes. But roughly,
so you have this arc which is 4 kilometers long.
Yes.
But the measured length would change basically depending on whether it's a crest or a trough.
Yeah, definitely.
Change you are saying is about on this one.
Yeah, all of this order. Yes. Yeah.
Okay. So most importantly, it's the amplitude of the wave we are measuring. Not we are not measuring the gravitons or photons kind of things.
Yes. Okay. All right. So now all of these plots that I showed, they come out of the numerical relativity simulations, and because of that, they are very clean. I mean, they are difficult and complex, but still they're clean. But when we actually see them in the detector, there will be noise. And this was the time series that was detected for the very first event, which was also a kind of a loud event. So the signal to noise ratio was much larger. So just by looking at the eye, by eye, you could say that there's something that looks like gravitational waves, and there's some noise. But in typical cases, you won't be able to say that, like the gravitational wave would be hidden in the noise and you have to extract it out. Now, whenever there is gravitational waves, then what you can do is that you could do a time frequency spectrogram. And because we have 2 detectors, or at that point we had 2 detectors, you have 2 different spectrograms. And in these spectrograms, you would see that there would be some points where there would be kind of a track where you have excess power than the surrounding points, and that would indicate that there's a signal. And once you have that, then you do the next step, which is a crude way of figuring out whether there is a signal that is described by general relativity, and if yes, then what are the parameters in a very crude term, right? So what you do is that using those simulations and other means, you know what a gravitational wave should look like when you vary the physics of the system. And by doing so, you would create a template bank where you would have discrete points coming from different binary black hole configuration, and you would save them in somewhere, and you call it a template bank. And then you have the signal that you have detected, and you think that it may have the actual gravitational wave. Now you would pass it through this template bank, and you will try to figure out that whether for any of these points you get a good match. And if you get a good match, then you know that there is a gravitational wave signal. And this is kind of an example of that. So you have the 2 time series, the blue and the orange, which are the actual gravitational wave data detected at the detectors. And then it was passed through a template bank for this guy here. And then there was a model parameter that there was some model time series that was found to be a good match to both of them, both of the data here. So that's where you know that there is a signal, and you roughly know their parameter values. Yes.
So the orbit and this direction of spin is what other parameters besides this going to the model?
Okay. So yeah. So there would be I should have said this before. So there would be 2 black holes. So the masses of them, so like 2 masses, then each of them could be spinning in any direction. So it's a spin vector, so 3 components. So like 3 spin for the first black hole, 3 spin for the second black hole. And then there could be the orbital parameters. So if you have eccentricity, you need 2 more parameters to do that. So In total, you'd have around 7 to 9 parameters. On top of that, you also need to know the distance of of the merger from Earth. You also need to know the angles on the sky where the merger is happening, and you need to know the time and the orbital phase. So that would be another parameter that you have to. So in total, it's like a 15 to 17 dimensional parameter space we are talking about.
So, and so are there no other events which can give rise to such graphs? Is it what? No. If you see such a graph,
Yes.
how do you if you
I see. So, right. So we typically expect that only like in that regime, the binary black holes described by general relativity would give rise to this kind of signals. Apart from that, even noise in the detectors can also sometimes give rise to this kind of things, and people study those things and know beforehand that what they would look like. So there are other details and other checks that goes into figuring out whether this is an actual, like an astrophysical event, or this is a glitch. Like we call it like a numerical artifact in the detector, and we call it the glitch. So it could be both, and there are those checks that go whenever we see something, it goes through those checks, and then we have something.
So are there other astrophysical events also which gives rise to that?
Right. Okay. So maybe not in the same frequency, but for binary neutron star merger, like if you have two neutron stars, they are merging, they would also give similar things. But the frequency could be roughly around the same range with a little bit of ups and downs. You can also have those from some exotic events, for example, boson stars or like something that is beyond general relativity. So that can also happen. Yeah.
How do you exclude those out? So
That's a little bit difficult because we don't have very accurate simulations for those, but we know roughly some theoretical expectation of what would be the corrections and all. So we try to look for those corrections in the data in a post-processing state. No, yes. Yes.
So this the whatever is written on the top, should I think of that? I mean, since we have multiple detector across the earth, should I think of this as an average value that was detected by all of them? I mean, is it some combination, or is this what you see in one place?
Right. Yes. This is what you see in the one place. So if you have three detectors, many times you will see the event in three detectors also. Right, but sometimes you might see them in two detectors or in one detector if one of the detector is down or something else is happening. But in principle, if there is a gravitational wave, it may show up in all the detectors because there is no detection in gravitational waves. So like all of them should pick it up if they are loud enough.
So if you can go back, he has a plot very clearly. No, I think.
Oh, I see. I see what you mean.
Here,
like here, this guy. Yeah.
There are two color plots out there, blue and whatever, yellow or something. Right?
Yeah. You and
those
orange.
are two independent detectors. They are 3,000 kilometers apart. So in order to bring them together, you have to give this delay. Because
because neither of them looks like that. So I was just trying to get a sense of what is that.
Oh, okay. Right. This one.
That's okay. So that's sort of a raw, and this is about massaged after the, after the match filtering and all that.
I see. Okay.
If you want to think that way.
Okay.
So.
So in some sense, like this is like some denoised version of whatever that was.
Yeah, and not even just denoise one. They have moved the time delay, because that because you can see that it's on the same time axis.
Sure.
So and not just that, two interferometers you have to flip by 90 degrees because there's an orientation.
Okay.
We put it by hand. The two interferometers are 90-degree flip.
Okay.
So that in order to avoid any accidental noise-induced signal correlation and many other things happen.
Also, this matched filter you said is some several dimensional, right?
So the match filter happens in a much reduced dimension.
But what is the number of parameters of the match?
So in the match filter, it's currently it's 3-dimensional to 5-dimensional, right? Because many of the extrinsic dimensions, for example, distance, angles, and so on, you know it analytically, so you could like marginalize them
You don't discretize the space, that three-dimensional space, you don't discretize.
No. So yes, so three-dimensional space is discretized.
All batch filtering are based on theoretical waveforms, which are purely almost analytic. And there are ways of doing that, but those are restricted to a circular, aligned spin, maybe a bit of eccentricity. The complicated thing which numerical activity can bring in, but those are not possible, and hence the reducer.
Okay. All right. So once we kind of detect a signal and we know that where the signal lies, and the match filtering that gives us a crude estimate of the parameters, but it does not include the full physics as Goku was saying. And so the next step is to include the full physics. And for that, what we do is that we do a proper Bayesian inference analysis of the signals using some models. And by model, what I mean is something where you just give it the masses, spins, and everything, and it gives you the radiation time series immediately, and you use that time series in a Bayesian likelihood to figure out the likelihood, and then you sample it across parameter space and figure out what would be the parameters like masses, spins, eccentricity, distance, and everything of the system in a probabilistic way. And this is something what you typically get, and this was for the first event, like the masses are around 36 solar mass and around 30 solar mass. So this is what we do, and this is where our importance of having a faster model comes in, because when you do numerical activity, as I mentioned, that it takes like a day to many months to do the simulation. So you cannot really use numerical activity to do a proper Bayesian inference here. So you have to have something faster. And there are some alternatives, like you could use some semi-analytical methods and something like that. But the accuracy of those methods would not be very great. So often you may get like biases and all. So that may complicate your analysis and astrophysical inference. So and maybe this plot would tell you why. Okay, so this is kind of a histogram showing you the accuracy of different kind of models we have at this point. So we have numerical activity, which is taken to be the most accurate simulations that we do. And in numerical activity simulations, we have around 1,500 to 2,000 simulations that we have done so far. And for each simulation, we actually do like a multiple simulations with varying grid size and everything to also know what is the numerical error in our simulations. And then for all of these 2,000-ish points, you can come up with one number that describes the average error in the simulations, and you plot that number for every one of them, and this is the distribution looks like. And then we have the data-driven methods, which we call the surrogates, which are trained directly on the numerical activity data without making any physics approximations. It just interpolates the numerical activity data in an efficient manner, and the accuracy of that numerical activity surrogates when tested against the actual simulations is plotted here. So it's overlapping with the numerical errors of the numerical activity simulations, meaning that whatever would come out of the surrogate models, that is indistinguishable from an actual numerical activity simulations, but you get that accuracy and the flexibility of generating those radiation profile at any point at the cost of 0.1 second instead of 5 months. So that's what we can provide with the surrogate model.
What's the bias?
This is a probability, so the density is like marginalized.
But probability over what? Like so over the.
So this is the model errors.
Yeah.
So I have like 2,000 points.
Yeah.
And then I plot
this is a histogram.
Yeah, they integrated to be, yeah. Okay.
Hi, I have a question. So how is it possible that the surrogate does not have that tail which the numerical activity has?
It also has a tail here, but so the way we interpret it this way. So when we calculate the errors in the numerical activity, we calculate it by doing different grid resolution runs and we then compare the highest resolution and the second highest resolution in the simulation.
Okay.
So in that sense, the error that I'm plotting here for the numerical relativity is the numerical truncation error in some sense for the second highest level simulations that we are doing. Now, but the error that in the surrogate is tested against the highest resolution runs we have. So this is not exactly an apple to apple, but this is the best we can do. Yeah, so but it's like these errors are slightly different in terms of interpretation. Yes.
This extractions is also changed, right? It's 1000 M
Yeah, yeah.
extraction also.
Right, right.
Do you do this hyperboloidal
We do that. So yeah.
and the semi-analytic is IMR?
Yes. So semi-analytic here is the effective one-body models here. Yes. Yeah. Okay. So the point of this here is that the surrogate errors are overlapping with the actual numerical errors of the numerical relativity, the best known simulations we have. And the other models, which are the semi-analytical models, are 1 to 2 orders of magnitude at higher errors than what numerical relativity surrogates can provide. Okay. So, yeah, with that, I'll briefly.
Numerical is like a fractional error in something, fractional error in amplitude of strain or.
Right. So these are the errors between the like the model and the actual numerical relativity.
Like we have a waveform.
We have a waveform.
Right, so this is a fractional error in the amplitude of the.
This is the integrated error. It will integrate
whole
over the whole frequency range where the detectors are sensitive.
Is it fractional error?
Delta
H over H, or is this just delta?
Okay, let me.
Probably delta H over H, right?
Yes, this is this is fractional. Yes, yeah, fractional and then weighted by the noise curve that we have in the detector.
So then the question is, what is the error that you are comfortable with?
Right.
So 10 to the minus 4 is too, it is like very, very precise.
Yes.
But you're probably not interested in that precise. Maybe 1% is enough.
Right. So if things are 10 to the power negative 2, then you are doing an okay job. In that case, if the signal to noise ratio is around like 17 to 20 signal to noise ratio, you would get biases in your like inference. So 10 to the power negative 2 is okay, but typically we want something which is like somewhere around, let's say, 5 times 10 to the power negative 3 and below. So that, I mean, for all of the LIGO Virgo events or the events that we see, you would not be biased. Like for the semi-analytical models, many times their estimations would be biased.
Those parameters you can tolerate, right? If it's black hole is 30 solar mass or 31 solar mass, you don't need.
Yeah, 30 to 31, you don't care. That's fine. But it could be from 30, it could be like 20. And like if you have 100 or 200 events, and you combine them together to understand the population of black holes, you would be very biased. Yes.
You are saying that 1% error can give you 30 to 20 bias?
If the signal to noise ratio is high, let's say 30 or 40, then yes. It depends on the signal to noise ratio.
I have the impression that other than the chirp mass, most of the other quantities are 10% errors, right?
Yeah, but with an error like this, like we have done the analysis and we found that for multiple events, like for example, I think around 10% of the events, your ratio of the masses would also be very biased.
Yeah, that's the chirp mass will still be okay, but the mass ratio will start.
Yeah, chirp mass would still be okay if you have really long signals. Yes. If not, then it would be not. Okay. So now I'll briefly describe what we do in building these surrogates. So we start with the discrete simulations that we have performed within the simulating extreme space-time collaboration. This is a multi-institution collaboration between Caltech, Cornell University, and some other institute, including Max Planck. And we do all of these binary black hole simulations, and this is the parameter space that we have. So that's the ratio of the two masses of the black holes. And these two are like the spins of the two black holes, like how rotating the black holes are. And you could see that it's quite discrete. So there are some points, like it's not really continuous, like especially in the high mass ratios and high spins, you have lesser number of points. So now what we want to do is we want to use these simulations. We don't want to assume anything. And then using these simulations, we want to come up with an efficient interpolator so that we can now generate waveform or radiation properties at any point in the parameter space that I'm showing here.
So maybe you just want to tell them that the mass is just a scale. So
Okay, yeah. So yeah, sorry. So one of what Gopu is pointing out is so in GR the total mass always scales out. So when we build this, when we do these simulations, or even when we build the surrogate, we do not consider the total mass. Rather, we keep the total mass to be 1, and then everything is controlled by the mass ratio. And then if you want things for 20 solar mass or 40 solar mass, you could always scale things to that total mass. So that's how we do it. So GR helps you a little bit in terms of the total mass direction.
In these models, now you're only considering mass and spin.
Yes, this is just for demonstration that what our points are in the parameter space. But when we build the model, we have multiple models, and for one of our models, we have like mass and the spin vectors, like both the spin vectors, so like 7 dimension.
But the original numerical relativity that is like 15, 17.
No, so that would also be 7 dimension. If we include elliptical orbit, that would be 9 dimension. But everything else are the extrinsic parameters. They are not the properties of the binary, like the distance from Earth, the angle on the sky, the time at merger, and other things.
Where you remove to the matched filter parts.
Yes, that is marginalized, and even when we do Bayesian analysis, so we know those by like analytically we know what they should look like. So there's no reason to simulate those. Okay. All right. So now we have all of these discrete waveforms, and these waveforms, what I'm showing here is that they're the simple looking waveforms. So, but in reality, we would have precessing spins, so they would be spinning generically, and it will have more structures. Now, the challenges in building these surrogate models here is that unlike in some other fields where you can generate a lot of training data. Let's say if your simulation takes an hour or 2 hours, then you have the flexibility to generate 1,000 training data or 4,000 training data. And if you find that that's not enough, then you could go to 10,000 points and then you build a surrogate out of it. But now in gravitational waves, we are working in a data scarce field because many of our simulations take 6 months. So it's not possible for us to do 5,000 simulations, and if we find that, okay, it's not working, then do another set of 5,000 simulations. Of course, we can do that, but it will take another decade for us to do that. So we have to come up with something where whatever we have, let's say if we have 1,000 simulations, using those, we can build the surrogate very efficiently. Or in some cases, we might just have 100 simulations. So our goal in building this surrogate is to build the efficient surrogate with as less number of simulations as we can, and that's what and for that what we do is that we often take some inspiration from physics, and I'll describe what we do here. And then the second thing is what I was pointing out previously is that we really need extreme precision. Like if our model is 90% accurate, in most of the events that we see, all the estimations of the binary backward properties would be biased. So 90% accuracy is not really a good thing for us. Like 99% accuracy is okay. Like that's where we really want things to be. So we have limited set of simulations, and then on top of that we have to be really accurate. So this is mostly the problem that we are dealing with, and then I'll show what we do for that.
So what's the signal to noise ratios you see in these waveforms?
Right. So that would depend on the sensitivity of our detectors. So currently we typically see a lot of events where this signal to noise ratio would be 8 to 15, but there are also a significant number of events from 15 to 30. There are a couple where like it's the signal to noise ratio could be around 40. So
So this is from log scale or something? What is, you're just dividing the L2 norm signal by the L2 norm of the noise. Is this?
right, yes, yes. Okay. So one thing that you can do when we say that efficient interpolator is that you take all of this radiation time series and you can have something, let's say Gaussian process regression, or you could have a neural network here and then hope that they would give you something which is working. So that's one way of going. However, that may not be the best way of doing things because then the neural network or whatever you come up with, it has to do many things on its own for your behalf. But rather, if you know the system, if you know about the signal and the radiation profile well, then you could help this modeling a little bit because you have to do a fit. So instead of doing a very crude fitting and hoping the fitting will do something, you could help the fitting in such a way that it makes the life easier for the fitting methods or whatever you are using. So what we do here is we use some physics. We do not assume anything about the binary dark holes in the like people doing semi-analytical modeling, but the basic physics we use those to decompose the data. So we pre-process the data in some way, and once we decompose the data, then we do a model order reduction. And using this model order reduction, we then figure out the most important directions that we have in the radiation time series. And once we have the model order reduction, then we do the fit. So by the time we come here, the fit becomes much more easier than if someone want to fit at the start. So that's how, using very limited set of data, we can match the actual accuracy of the numerical relativity simulations. And the first point is to use the physics. So instead of using the full radiation profile, what is typically done is we look at different mode contents of the radiation. So you decompose the waveform into multiple spherical harmonic modes, and typically the 2-2 mode carries most of the radiation. So, and people in earlier days used to only model the 2-2 mode, but now we model as many modes as possible. The semi-analytical models, they have around 5 to 6 modes. In surrogates, we have around 11 to 12 modes that we try to include. So the point here is what we do here, instead of building one crude model, we decompose them in multiple modes. Let's say typically we have around 10 or 11 modes. So we have like 11 decomposition, and then we would build submodels for each of these modes. So we are simplifying the problem.
So that radical relativity simulation gives you all of these modes?
Yes.
It does not give you just a full final waveform, it gives you.
Yeah, it tracks the radiation and then decompose them for us. So it tracks the full radiation. Yes.
So you're solving the differential equation, now you're solving for the decomposition.
No, you are solving the decomposition. Yes. So radiation, you solve it once.
So
and then you
the
decompose.
differential equation is only in terms of the full wave.
Full range. Yeah.
So from but you now want to get like.
Yeah, so this is so coming to the modes is very simple. It's you know the angular profile, so you just it's analytically you get all of those things. Yes. Okay, so you simplify the problem a little bit, and then for each mode, because I already mentioned that this is like there are two polarizations, so you describe your signal as a complex number, so that you have information from both the axes, and then because it's a complex time series now, instead of modeling the complex time series, which is a difficult thing, you can say, okay, I'll model the real part of the complex time series and the imaginary part of the complex time series. However, that's also tricky because you have a lot of oscillatory behavior, and the oscillatory behaviors are very difficult to model. So instead of that, you say that I will decompose it further. So you take your complex time series and then you take the absolute value of that. So that gives you the amplitude, which looks very simple like this one. And then So note here that I'm not including eccentricity here, so they look simpler. So I'm just, we also do all of those kind of things, but I'm showing a much simpler picture for us to understand. Okay, so we get the amplitude, which is the absolute of the complex time series, and we get the argument of the complex time series, which is the phase. It looks better than fitting this guy here. So we have, for each mode, we have 2 mode decomposition. So now one model, instead of modeling one thing, we first decided we will model 11 modes separately. And now we are saying we will model the 11 amplitudes separately and 11 phases separately. So now we have 22 submodels. So we are breaking down the problem piece by piece.
So
Yes.
just a follow-up. So some of these modes were equal masses are essentially zero.
Yes.
And you actually see that from the extraction.
Right, exactly. Yeah. And when that happens, we exclude that from the data.
So that zero is different. I mean, when you extract these things, you will find something. But
Right.
So distinguishing that from the noise and all that is
true. So what we do, let's say if we are building things for only equal mass, then we do not model them at all.
Okay.
But if the black hole masses are asymmetric, then we keep them as they are. And we found that the surrogate has learned that they are numerically zero and gives you something which is numerically zero.
Okay, that's what I was.
Yeah, but they're not exactly zero, it's numerically zero, yes. Okay. Okay, so now we have simplified the problem up to this level, that we will only model the simpler looking amplitudes and simpler looking phase. And then we'll do a model reduction. What we will do is that we will take for each mode, we will take the amplitudes of all of the waveform, and that will give me this particular metric A here, where I'll put all of them together, and I will take a singular value decomposition of that. And that will give me the basis vectors that represents the lower dimensional space for the amplitudes for each mode. And this is a much simpler problem now. And then what we'll do is, now at this stage, of course, you could say that, okay, so I know my basis vectors for the amplitude, so I'm focusing on for one mode, one amplitude. And then I know the basis vector, which means for each of the point, I can then project the amplitude on the basis vectors. That would give me the coefficients. So I will have the coefficients for all of these guys here, and I'll just build a fit for the coefficients as a function of the parameter space. So that is one way to do. However, we don't do that. What we do is that we decompose the problem further. So because if we do that, then what we'll have, it's not a bad thing. I mean, this is something we also do that, but typically the basis vectors will have many time points, and you will have to build a fit for each of the basis vectors and their coefficient across the parameter space. But one of the reason people were afraid at the beginning was that we are solving a binary black hole problem, which is described by general relativity, which is a nonlinear theory. So a binary black hole problem is also a nonlinear problem. And when you use singular value decomposition, it tries to find out the basis vectors so that on an average, you get a good match. However, you are solving as a time series. So there could be points in the time series where the nonlinearity is strong, and there could be points where the nonlinearity is not strong. So when you get the basis vectors out of the singular value decomposition, points where or the time values where the nonlinearity is strong, it would fail to capture the full physics. So instead of using the SVD directly here and solving a regression problem or the fits.
So what do you mean that some points nonlinearity will be strong, some points it is like elliptical orbit where you are very close.
Right.
So when they are far away,
yes.
It is more linear.
I mean, not even elliptical, even for circular, when the two black holes are further, the gravity is weaker there. And so you could approximate it in a more linear fashion. But when they're very close to each other and when they're merging, so that's where the nonlinearity would be more important.
You are saying the final stages will not be captured by this.
Yes, so it's a possibility. Yes.
But you have the solace in the sense that EOB actually capture all that.
Yeah, definitely. Yes. Yeah. So with linearity, you could still do many things, and I'll show one plot at the end. But we typically don't do that under the assumption that maybe there's something and maybe we miss some of the information there. Because as I mentioned, our goal is to provide the numerical relativity simulations with the same accuracy, but in a much faster way. Okay, so what we do there is something.
In principle, you can capture some of the nonlinearity in your eigenvectors, right?
That's true. Yes, yeah. So we want to capture as much as possible in while building the models.
What are the dimensions involved in this generally? Like the single value decomposition is how many basis vectors?
So for the base model that we have that includes most of the physics is a semi-dimensional. But we have like different other models like one dimensional. The maximum is 7-dimensional. Right. Okay. So what we do is that we use the singular value decomposition. We use the basis vectors that we get out of the singular value decomposition. But now we do more. Instead of solving a regression problem for the coefficient, SVD coefficient across this parameter space, we now convert this whole thing into an interpolation problem. What we do here is that if you have a time series, your time series may have 50,000 points or 60,000 points. So we now ask the question that what are the most important points in this time series, so that if you know those points, you can reproduce the whole time series. And that then becomes an interpolation problem. And in the interpolation problem, we use all of the information that comes out of the SVD basis vectors. We use those, and then using those, we try to figure out what are the points where these SVD approximations are failing. And those points give us the most important points for nonlinearity. And then we use those. So what happens there is that now instead of 50,000 points, I get 5 to 7 points, which seems to be most important ones. And if you know those, you can know the whole thing using the SVD basis vectors that you have already calculated. So these are the, let's say, this is a very simplistic picture, but it would help to understand. So this is the amplitude basis vector, let's say one of them. And these are the 3 points that we have found to be the most important ones. And in most of the cases, we will almost find that there's 1 or 2 points around the merger where I mentioned that the nonlinearity would be stronger. So we find these points, which are called the discrete empirical interpolation points, or you could call it some magic points. So once you get the magic points, then what you have is that all other information about the SVD basis vectors and everything that goes into this B matrix here, and it calculates everything. So it becomes an interpolation matrix. And then that interpolation matrix will only take, let's say, n number of points, let's say 4 or 5 points here in H. And if you provide those points, it will give you the full time series. So that's more or less the idea. So we have made the problem even simpler now, and it's treating it as an interpolation problem rather than a regression one. And the next step is then, of course, build the parametric fits. Now, in building the parametric fits, what we are doing is that, let's say I have 3 or 4 EIM points. So I would build a parametric fit for each point across the parameter. So in my model, now I will have 22, I had 22 submodels, 11 for amplitudes, 11 for phase. And then for each of them, whatever is the number of these EIM nodes that we have picked, that would be the extra number of submodels. So in principle, if I have like 4 here, 4 magic points here, I would have 22 times 4, so 88 submodels. So the problem has become much more simpler than the initial point where we wanted to build the whole thing together as one block. And then if we look at a 1-dimension thing, so this is a very simplistic thing. Of course, we cannot visualize a 7-dimension thing. So I'm just showing a 1-dimension thing here. So I took one of these EIM point and I'm plotting them as a function of some parameter of the binary. And there you could see that they behave very smoothly. And you could build, and then you build a fit for those points here. And you could use a spline, you could use a polynomial to build the fit, or you could use a Gaussian process regression. So we typically use the Gaussian process regression for our fit because we found that they perform better and they could extrapolate a little bit outside of our training space where the simulations lie. And then when you actually generate, let's say someone would like to now use this model and they would like to generate the full radiation. So what you will do, the user provides you the masses, spins and everything, and then you will take all of those and would ship them to this EIM node GPR fits that we have, to 88 fits. And each 88 fits would now use this GPR fits or whatever to figure out what should be the value of this EIM point somewhere here in between. And you have for each of these basis vectors, you have something here in between. And once you have that, you already have created the interpolation matrix because you have done the SVD and all. You just use it to get the full time series. So you get, for each mode, you get the full time series of the amplitude and phase. You combine them, you get the full complex mode. You combine all of the complex mode, you get the full radiation. So you then start from the EIM nodes and come back to the full radiation. That's how our modeling works. So you break it down to so many small pieces, then the modeling becomes much easier than one could think at first. So in principle, if you had a neural network and if that neural network had to be really good, they have to do all of these things on their own in their latent space. But instead, you are just doing many of these things on your own. Okay. Now, I'll show a couple of examples. Yes.
So could you just outline what Gaussian process regression is? Does the process just model the noise? Or what do you mean?
Oh, I see. Okay. So the Gaussian process regression is, yes, so you have multiple points as a function of the parameter space. You have multiple like Gaussian kernels sitting around, and those values you obtain from those training points. And each training points, you allow them to have certain noise on top of it. So you also know the noise flow, and you combine all of these things. So you have a like probabilistic fitting.
So the Gaussian kernel has something to do with the covariance of the noise.
Yes, it also uses that. Yes. Okay. So now this is I'll show just a couple of examples of how good we could be. So this is an example that includes the full physics in the sense that you have the two black holes and their masses could be equal or asymmetric and their spin could be in any direction. And you have the actual numerical relativity data in black, and the surrogate prediction is on top of it. Except at the final part where we deviate a little bit. However, this particular case is our worst case. Meaning that for everything else, we will do better than this. But then if you compare the other models, which is a semi-analytical models, you could see how different those are from the numerical relativity models. And even when we show our worst possible case, this point is actually coming from here. So it's still within the error of the numerical relativity simulations. Okay. And then this is another model where you have the two black holes and they are not on the circular orbit, rather they are on the elliptical orbit. And for that, you have NR waveform here for different modes, and then on top of it, it's a surrogate waveform. But this surrogate is now extrapolating. So even when it's extrapolating, you could see that they're matching quite well. If you zoom in here at this part, you will see there's a little bit of difference. But for any other case where it's not extrapolating, it would actually fit the NR very well. And typically, whenever we show this plot, we do not show the training plot. So what we do is that for each point, let's say we have 100 points. So we build 100 surrogates. So each time we take 1 point out of it and then build this surrogate on the rest of 99 points and then use that to predict the held out data. And then we take the error there. So every time I show an error or I show a plot for how good surrogate could be, it's a validation plot that I will be showing.
Sorry.
Yes.
In this case, the number of modes will be also more than the 11 you are talking about, right?
No.
The eccentric.
No, we still have similar modes. Yes.
I had the impression that
No, but these are our spherical harmonic modes. So,
Oh, no,
right,
this is not coming.
right.
Okay,
Yeah.
okay, fine. This is it. Sorry.
Yeah. Okay. So this is more or less showing that the surrogate can recover the actual numerical relativity very well. Okay, and this is now another example. Now, this is taking the surrogate to the extreme. What is happening now is we are now modeling the binaries where their ratio of the masses are around 15. So they are very asymmetric. And still in there, the surrogate, which is this guy here, matches the NR pretty well for different modes. However, if you take a semi-analytical models, you could see that towards the end they deviate pretty much here. Okay, and okay, so that's one part of the modeling where we model the radiation time series. But there are more things. For example, when the two black holes merge, so you have seen in the video that I shared, is that the merger of the two black holes produce another black hole, and that black hole have a different mass than the and as well as the spin than the initial two black holes that we started with, and it would also have something called a kick. So it will get some extra velocity at the end of the merger, and it can move in any direction. So we call it the kick velocity. So these three things are typically called the remnant properties. So we also model the remnant properties of the black hole mergers. So this would be point instead of like a scalar number instead of a time series, and we model all of them. And again, there you could see that the NR error and the surrogate error, which is the maroon looking line here, they are on top of each other, basically reproducing the NR error. But then there's a couple of semi-analytical models that we have. And if you look at their errors, there's a 1 to 2 orders of magnitude difference in terms of the accuracy that we have. Okay. So now, in the next part, we are not now building the surrogate, but now we would like to use SVD in understanding or extracting something which we think is physical. So it's more like an abuse of SVD that you can do. So maybe like about 5 more minutes. Okay, fine. Okay, so what we do here is that, let's say if the binaries are on elliptical orbits, then you have those extra oscillations or modulations that you have in the system, and it makes your modeling difficult. So what you can do is that you can try to find out something simpler, structure that is hidden behind this modulated time series here. So if you take a time frequency spectrogram of that, then you find that this signal actually has many time frequency tracks, which means that it has many subharmonics within it. Now, if you do not have a theory to guide you properly, what is going on here? So I know Gopu has some of the calculations, but those calculations are not readily available in the models that we have. So or even in the numerical relativity simulations. So what we can do is that we use the singular value decomposition, and we force it to extract those time frequency tracks. How we do it is that we know that if the two black holes are on eccentric orbit, then you need two parameters to describe them. One is, of course, how different it is from a circular orbit. We call it eccentricity. And then the second thing would be related to a phase of eccentricity. Or in other words, you could think of like where these two black holes are on the orbit. Now, depending on that, there will be some differences in your radiation profile. Now, this tracks only exist whenever the black holes are on elliptical orbit. But if they are on circular orbit, they are only one of them stays. Everything else they vanish. So what we do here is now we restrict the problem and we create a sample of radiation time series where everything else is same, except we put the binaries in different points in the same elliptical orbit. So that now creates an example of radiation profiles which has the same orbital structure, but with different phasing. And then we create, and this is how our all those like many samples look like. And now we pass this to the singular value decomposition. And then the singular value decomposition, typically it figures out the orthogonal directions, orthogonal basis vectors, but there is no guarantee that whatever it picks up has some physical meaning. But here we are forcing the SVD to pick up some physically meaningful basis vectors, and that is exactly what happens. So SVD picks up all of these lines separately. So each basis vector that corresponds to each of the line that we have seen in the spectrogram, and then the result is shown here. So the original waveform is very oscillatory, and with the peaks have ups and downs. But then if you look at the what the SVD picked up from J1 to J4, so these are the subharmonics, you could look like they are much simpler looking. So you could abuse SVD to give you something which is much simpler in terms of the time series behavior in the radiation profiles, and then instead of modeling this whole thing, you model all of these subharmonics separately with the help of the SVD. Okay, so with that, I'm at the end. So I mentioned here that when we build the fits across different points for each of the EIM node, we typically use Gaussian process regression or splines or something. So splines are a bad thing to use because they extrapolate really bad, because they do crazy things at the boundary of things. So instead we use Gaussian process regression because it seems to be doing a pretty good job. But if you have many samples to train, let's say 1,000 samples or so on, then the Gaussian process regression has a large evaluation cost. So it goes like n to the power 3 or something. So it's not really a good thing. So it's still like 0.1 second, it's still great, but you could do better. So a better thing would be if you can use a neural network. But using a neural network is tricky because at least all of the studies that people have done with neural networks so far, you need 50,000 points or like 100,000 points or even more than that. We do not have that many numerical relativity simulations, and we would not have it in the next 10 years. So what we can do is we use the surrogate that we have built to populate this parameter space more, and then use the neural network, which once built is much cheaper to evaluate. So then you use the neural network to build the surrogate of the surrogates. So now you have the same accuracy, but your evaluation cost, instead of 0.1 second, it might be 0.01 second. So you are gaining a lot in terms of the analysis timeline that you'd have.
Can you use Chebyshev polynomial? They're also going to be computationally expensive.
You could use, but we also explored that. It seems that it gives a larger error that we have. Yes. All right. So we figured that out. But now there is the final problem, which is, let's say you have 10 or 50 numerical relativity simulations and you want to build a surrogate for all of the radiation profiles. Now, if one of your waveform or the radiation profile is, let's say, 4,000 m long, and the rest of them are 10,000 m or 12,000 m long, your surrogate duration video or anything else you like with the high dimensional parameter space. So that gives you the basis vectors. And then you use the cheap simulations and you project them on the high dimensional basis vectors. You get some coefficients which would be slightly biased. But then you would learn the bias from the data. And in the final way, final step, what you do, you'd have a regression over the cheap coefficients that we have got, and you'd learn the bias and you'd put them together, and now you have a surrogate that you have built with very few high accuracy simulations with the help of low accuracy data, like dense data points that you have created. So now we use that for this surrogate. So what we do is that we select some of the longest simulations that we have in our system. So maybe they are 10,000 m or 12,000 m long in the unit of total mass, and we use those to create our basis vectors. And then we have the rest of the data that are much shorter, like 4,000 m long or 5,000 m long, and we project the shorter simulations on the basis vectors that we find here. We learn their coefficients, and here the good thing is we don't have to learn the bias because they are all coming from the same physics and the same high accuracy simulations. So there is no bias in their coefficients. So all you need to do is now build a parametric fits for the coefficients here, and then you will have the full surrogate, which is much longer than 90% or 95% of your simulations that you have created. So that way you can, even in terms of your training data generation, you could be really cheap in that. Okay, and this is a quick example. So this is some error that we use to know how good our surrogate is. And these points are linear surrogate, hybrid, and those are the typical surrogates that we have built so far. And the multi-fidelity surrogate fits right on top of the older data, suggesting that we can have the same accuracy, but now we can have a much longer surrogate, and that would be like mitigating one of the limitations that we had so far. Okay, so with that, I think that I'll stop here. I probably took some more minutes, but yeah, so like we're building surrogates for gravitational waves, and we know what we are lacking at this point, and we are actively working on fixing those things. So yes, so, yeah, thank you. Thank you.
So here, I mean, one of the main ideas seems to be that instead of like learning the function, you try to learn some linear transfer. Like in this case, the spherical harmonic coefficients, right?
Yeah.
But this could be a more general thing. Like if there's some other symmetry, you could like to decompose.
Yeah, sure, exactly. Yeah. I mean, not necessarily that we have to use the spherical harmonics, but
something, whatever is the light basis.
Right. Yes.
So, has it been, has someone tried using that neural network, tried implementing a neural network over the data set? I understand it's small, but you can again populate it with the model that you use.
Right, exactly. So that's that's what we are working on right now.
But what about replacing the entire pipeline, just putting neural nets?
From the start?
From the start. But you can fill in artificial data using the
Right, yeah.
You can gain them less because they are artificial.
You can do that, yes. So we are implementing the neural nets, but we are not implementing the neural nets from the start. We are still doing the same decomposition, except where you used to do the GPR or something else. We're just replacing that with neural network.
So if you train if you populate the data set with artificial data from the surrogate models,
yes,
maybe weight them a bit less than the actual data.
I see. You are saying that can be done. We don't do that at this point. But yeah, you could provide an error along with the data.
Will it be faster than this, or is it?
Yeah, with neural net it would be faster because the evaluation time is much faster than GPRs and other things.
And also, do people work on speeding up the numerical relativity simulations? Or is it not possible because it's PD and you have to solve it?
People do work on that. It's a slightly difficult because it's a coupled partial differential equation, so there are many pieces. So like oftentimes some pieces run faster, some pieces run slower. So I mean, so far people have not been very successful in doing so.
Yeah, you have to do it sequentially.
Yes, like many parts of the code just has to wait for other parts to get finished.
Thank you.
Okay, that's fine.
Okay. Yeah. Actually.
So I have a question. So when you said that